Hello and welcome everybody. My name is 𝗕𝗃𝗀𝗁𝗃 from University of Ljubljana, and prior to introducing today's speaker, I would just like to inform you that this section is being recorded and the recording will be available later. All the videos of the Thermal Transport Cafe sessions so far are posted and available on YouTube, and I will post a link after Axel starts the presentation. So it's my pleasure to introduce you the speaker of this session, Dr. Axel Sielaff from Technical University of Darmstadt. Dr. Axel Sielaff graduated in 2008 in the University of Hanover and later joined the group of Professor Peter Stephan at the Technical University of Darmstadt. And under his supervision, he completed his PhD in 2014 in the topic entitled Experimental Investigation of Single Bubble and Bubble Interactions in Nucleate Boiling. Since 2015, he's heading the Boiling and Evaporation Group and is responsible for the entire experimental test field in the Institute. Main fields of his research are phase change heat transfer, wetting and dewetting, especially on complex surfaces, simulations in the field of nucleate boiling, and of course, he devoted a large part of his scientific career to investigate phase change heat transfer in microgravity, especially boiling performed on parabolic flights and International Space Station. I personally met Axel in one of the kickoff meetings of the European Space Agency project, Multiscale Analysis of Boiling. And I can say it's always a great pleasure to discuss and learn from him, not just about the fundamentals, but also about the technical points of view, how to perform experiments in different environments. Last but not least, Axel played a very important role in design, build, and successfully run the Ruby experimental setup, which was placed on board the International Space Station and successfully executed more than 3,000 experimental runs. Much more about that will be presented today. So Axel, please go ahead.
Thanks, Sielaff. Thanks a lot for this nice introduction. Yes, it's my pleasure to present the project, which had been performed in a huge group of researchers and research groups. So it's not just my work, also your work, Sielaff. You also joined this work. So yeah, but maybe let me start. Boiling, yes, I named the talk Multiscale Boiling, Better Understanding an Everyday Process. But I want to start, let's say, with a small video, how we also started our multiscale boiling experiment. Hope the video will run.
9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition.
And what you can see here is our experiment on a Falcon 9 rocket on its way towards the International Space Station on 25th of July in 2019. So doing such experiment, quite a lot of effort, also quite expensive. We have to ask ourselves the question, why we do this, why we do boiling research, why we do multiscale boiling research. And boiling is a process that happens everywhere. It's a quite powerful process, not just in nature, like we can see in here. It's also used in a huge amount of technical application, and let's say together with its small brother evaporation, it's used in every consumer electronics, what we're using right now, looking at this video, in every refrigerator or fridge. We use it in heat pumps, or also AC components for your apartments or for our apartments, in data centers, high power computers. We use it in chemical industry, in power plants. Also, the fuel for a turbine has to be evaporated before it gets burned. And also, for example, in air conditioning of cars, we use boiling processes. So one may ask the question, if all these processes are running right now and today, why we do have to still do research on boiling? And I just want to give you two examples of that. Looking, for example, for the air conditioning of a car. So nowadays, if, for example, like European Union some years ago banned a refrigerant by global warming issues, we cannot just change it on your next maintenance. You have to build new evaporators. These evaporators will build into new cars. They have to be bought to the people. So changing maybe harmful refrigerant could take 10 to 20 years until all of the old refrigerant is, let's say, away from the streets. So yes, and wouldn't it be nice if we cannot just go to the next maintenance, change the refrigerant out of the cars, recycle it in a good way, and go on with a new refrigerant in the same car. One other issue why we can use boiling in so much applications is that we can also build prototypes. So keeping the same example, building an air conditioning device or evaporator, maybe for a car which will bought 100,000 times or even more, we can build easily 10 or 20 or even 50 prototypes. It's not a problem. But for other issues, for example, if you go to space exploration, if you want to go to Moon or to Mars, maybe it would be nice to know that this boiling process will work without building 10 or 20 prototypes, which you cannot test on Earth because you do not have the opportunity for a long time Moon or Mars gravity environment. So the only thing we can get is up to 30 seconds in parabolic flights. So there's also one point where we can see that the boiling process is not really well understood so far. So, but yes, why we can do that today, despite the huge amount of applications we have in the field, and the answer is more or less easy. In all the correlations you use for design boiling equipment, all these correlations are just looking into partial areas of the boiling process. One focusing maybe on the heated properties, other focusing on the parameters. There are also correlations focusing on gravity. But yeah, all the correlations are not keeping or not giving us the whole picture of the boiling process because it's just too complex and not understood up to now enough. I don't want to go into detail to the all correlations. I just want to give a small motivation. So I will not show correlations, but just let me show, let's say, how we want to proceed in this way, because the boiling process is more or less based on 3 columns. We have the heater, we have the fluid, and we have the boiling parameters. All of this we can divide further. Heater has material, it could be copper, steel, aluminum, whatever. These materials have material properties, density, heat conductivity. The heater has some form, could be tube or flat surface with a structure and roughness, a porosity. The fluid for sure also have material properties like density, viscosity, surface tension. And also we have the boiling parameters like pressure, heat flux, gravity, orientation of the heater, and much more I haven't put on the slide. But now looking to, let's say, up-to-date correlations of pool boiling, we will see that, for example, the contact angle is one of the major parameters, but it's not a basic parameter, let's say, out of this list, because the contact angle is influenced by a lot of parameters, even of different columns. So it will be influenced by surface energy, roughness, porosity, surface tension, pressure, heat flux. Just to give you an example, that it's not, that it's very complex, and that we try to go, let's say, down the slide to separate all the influencing parameters from each other to get a better overview over the whole process. For sure, I mentioned also on the first slide, experiments like this we cannot do on our own. So let me just spend a few words on our research partners. The whole Multiscale Boiling Project was financed by ESA. So we have most cooperating partners from Europe. So from France, from Greece, from Italy, from Belgium, also from Russia, and we also have international partners from the United States and Japan. And the whole project was afterwards built by Airbus Defence and Space in Germany. And the experiment has been performed by the PSOC in Brussels. So I don't put all the names. A lot of people are even in the talk, but yes, just to let you know that I haven't done this on my own for sure, and it's a lot of work of a lot of people. And I also want to thank all the other colleagues for the good cooperation. Another question is why we do these experiments in weightlessness. So we can also do lab experiments, but why we go to space or into parabolic flights. Therefore, I just want to show you a small video. It's the same experimental setup. It's a multiscale boiling cell. Same parameters, except of the gravity, just the 𝗕𝗃𝗃𝗁𝗃 was implemented in 2 of the cases. I will come back to this later. But if we look to the boiling process, we see a clear difference by gravity. So on the left side, we have 0 gravity, nice circular bubble growing. It's not detaching from the wall. In 𝗠𝗃, the bubble is pressed towards the heater. We have a quite flat bubble. And in 𝗠𝗃, we have really, really tiny bubbles leaving the heated surface quite fast. Next to it, I want to draw your attention to 2 points. I will come back later on in the talk. Okay. By the way, can you see my mouse? Hopefully. That's good. Here you, for example, see a huge patch of a reflection because we have a flat surface on the bubble. And here, for example, in this area, you can see this 𝗕 caused by natural convection in the pictures. And just keep that in mind. I will come back to this later on in the talk. So why we go to gravity? As I've shown in the slide before, gravity itself has a huge effect on the boiling process, but it's not just that, because also the other influencing factors are sometimes covered by the influence of gravity. So for example, if you think about density, the difference in density from liquid to vapor is huge. So having the gravity, this will cover a lot of other processes we cannot observe in 𝗠𝗃 boiling experiments because the influence of gravity and thereby also the density of the fluid or difference in density, it's just, yes, covering all the other influences we want to observe. So just to talk a bit about the motivation of our project. So what is our project, what we do? First of all, to bring the project to the International Space Station, you do some experiments in the lab. Next to it, you do it on a parabolic flight, and afterwards you do it on the International Space Station. It also means that you have to bring an experiment with about 3 cubic meter of size for parabolic flight into the size of about 1.5 cubic meter. On board the International Space Station, you have the size of 2 shoeboxes, implementing even more equipment than the parabolic flight. And here you can see the opened experimental container of the Multiscale Boiling Experiment in the Airbus lab with the project leader, 𝗬𝗪𝗪𝗁𝗪 and the project engineer, 𝗕𝗪𝗪𝗪𝗪𝗪𝗪, who built the experiment. This is a quite huge task to shrink the whole experiment down to fit inside the given size on the experimental space, on the International Space Station. So just give you a quick overview how the experiment works. So here you can see a schematic of the main components. In blue, you can see the fluid. In gray, it's a cell. And we have preheater and condenser to heat up and cool down the fluid, the pump and the bellow. As you can see, the whole volume is filled with liquid. So by using this bellow, we can set the pressure in the system to the desired pressure we want to have. We want to start an experiment. We shoot the laser to the center of the superheated, of the coating, which will superheat the fluid. So the bubble will grow. And another thing we have in the Multiscale Boiling Project is that we can also have external forces. So if we want to have a shear flow, we can use a pump to implement a shear flow so that the bubble will slide over the heated surface to the side. We can also use an electric field as an external force to the bubble. So an electrode can be lowered to the heated surface and we can apply high voltage electric fields. We can also combine this shear flow and electric field. From measurement point of view, we have a 𝗕𝗃𝗃𝗁𝗪𝗃, which you have seen on the first video, which could be brought down to the heated surface or back to the home position. So unfortunately, moving this device failed some time after beginning of the experiment. So we just got the data from the 𝗕𝗃𝗃𝗁𝗪𝗃 in the homing position. And for sure, we could observe the process with an infrared camera, high-speed infrared camera, and with a black and white camera, not looking under a 55-degree angle, but let's say perpendicular to the slide. So that we can see the bubble shape. You can see the heater assembly, which was built in our institute. We have an infrared transparent heater, which is coated by chromium nitride and chromium layer as a joule heater, and yeah, more or less just applied with cables to have electrical contact, and this heater is implemented into the boiling cell. One special issue of the heater is that we have a L-shaped cavity laser drilled into the infrared transparent crystal to ensure that vapor will remain in there when a bubble leaves the area by, for example, shear flow or electric field. So to operate an experiment on the International Space Station is also not just going there and turn some wheels. So let me take a few words how the experiment is operated on board the International Space Station. First of all, we have the 𝗕C, the experimental container inside the fluid science laboratory, which is a drawer within the Columbus module. The Columbus module is one part of the International Space Station. For sure, the Columbus module will talk to the International Space Station, but then afterwards, the space station will not send the data directly to Earth because the altitude of the space station is more or less 400 kilometers. So you would need a lot of stations on ground to transmit the data. So the data is sent to a geostationary satellite system. I think it was about 40,000 kilometers in altitude. Afterwards, the data is sent to Earth and then transferred to NASA in Houston. NASA in Houston automatically sorts out all the data which belongs to the Columbus model, sends the data to the Columbus Control Center in 𝗕𝗃𝗃. Afterwards, all the data belongs to the Multiscale Boiling Experiment, is sent to the 𝗕BSOC in Brussels, where you can see down here is the operator, yes, which is operating the experiment. So he can send commands, and he will get the answer on his command, which will take more or less about 1 second to send all the data to 𝗕𝗃𝗃, Houston, to the satellite system, space station, Columbus module, and the experimental container, and back to the operator. And here you can see also the first difference, let's say in the data stream. Here the data is splitted to the user home base infrastructure from 𝗕BSOC, where we as scientists can use the data, download the data, look at the live data over a VPN connection from our home computers. So what comes out of it? So I've also mentioned that we performed over 3,000 data sets on the International Space Stations. We had the two external forces, shear flow and electric field. Combining those, we have 4 major experimental combinations, and major change the parameter of subcooling. Here you can see the amount of experiments we performed with the given values of this parameter. So for example, the most parameters we performed was 5 Kelvin of subcooling, then 3 Kelvin, 1 Kelvin, and so on. We performed heat fluxes between 0 and 1.5 watts per square centimeter. 0 watts, we just looked at the influence of the laser when we shoot to the cavity. We varied the pressure between 500 and 1,000 millibars. The flow rate in the experiment had been changed between 100 and 700 milliliters a minute. For sure, not so many experiments because we haven't used shear flow in all of the experiments. The same with electric field. We varied it between 5 and 15 kilovolts in a distance of 6 or 8.5 millimeter. And the largest parameter we changed was the waiting time between 1 and 30 seconds. If you do an experiment like this, you have to ask the question if the data is reproducible. So it should be like that. And you can see a video. When we performed an experiment on board the International Space Station, we set a parameter range. And then we normally perform this experiment 3 times in a row to check if the data is reproducible. You will now see the video of such a data set. It's from pool boiling case, and you can see, especially in the first time of the bubble growth, when you put the bubbles next to each other, you cannot see a difference. Just when the bubble starts slightly to one side and the cavity is set free for further nucleation, then you see some fluctuations. The bubble are slightly different, but especially in the first seconds, you cannot see any difference in the growth of the bubble of the 3 different cases. Next question for experiment running over 11 months is if the data is long time stable. So doesn't make sense if you want to compare something and the data is not the same from the beginning to the end. And therefore, we implemented a so-called reference experiment with exactly the same parameters. And we performed it from time to time over the whole period of the whole campaign. And here you can see the data starting from 22nd of October 2019. So we plot the bubble diameter over the time. And you can see that the data is quite comparable, just at the last measurement sets at beginning of January 2021. We have a slight larger bubble diameter, which might be caused by non-condensable gases, but we have to check that later on when we open the AC. I talked about the external forces. For sure, I want to give you an example how the external forces act on a bubble. You will see 4 videos, same parameters, expected voltage and shear flow for sure. For a pool boiling case, electrical field case, shear flow case, and an electrical field with shear flow. So at 0 seconds, we also initiate the bubble by a laser. And you can see that for a pool boiling case, we have quite nice circular bubble, not moving, not detaching. If you go to electric field, we have an elongated bubble by the electric field, which will also detach from the surface. In the shear flow case, the bubbles will drift over the heated surface. Some will coalescence, some will not, depends on the parameters. And you can start the video again. If we look for electrical field and shear flow, we see that the bubble are first pushed out of the center of the electrode by the shear flow, and then the bubbles are also tilted to the left and accelerated by the electric field. We'll just finish the video. Okay, let me show you some first results of the multiscale boiling experiment. Here I took a pool boiling experiment and compared the different influences of pressure, heat flux, subcooling, and waiting time, always compared to a so-called or to the mentioned reference case, which is always marked wet. So here you can see what is more or less expected. If you decrease the pressure, the bubble will grow faster. If you increase the waiting time, so the time we heat the system before we nucleate the bubble will grow faster. It's the same for increasing heat flux, the bubble will grow faster. And for decreasing subcooling, the bubble will also grow faster, which is more or less expected. But you can also see the influence, also the significance of the different influencing parameters. While, for example, in this parameter range, pressure has not so much influence, but heat flux and subcooling has a much larger one. This can be also shown, this can be also seen on this graph, where for the bubble coalescence, 𝗦𝗽𝗰 performed this evaluation. So they looked if a bubble in shear flow case have a coalescence or not. And then they sorted it by the different parameters in a way that we get, let's say, large areas of the same color, where a green color means that we have coalescence in this case and in all subsequent cases, and red means that we know that we don't have coalescence in this case in all subsequent cases, and yes, gray resulting that we have both in the subsequent cases. And here you can see, if you want to arrange this in a way that you have large blocks of the same color, you have the same let's say, order of significance here: subcooling, heat flux, flow rate, waiting time, and pressure. Yes, to bring this data into the given into the graph. I don't want to talk too much about all the results, because from last week you can also read it in our new published paper. So you can just download it. We publish it open access. So yeah, feel free to download and read it, and maybe also give us some comments on that. But therefore, I want to use my last 7 to 8 minutes about the question where we are right now and where we want to go with this project. And here you can see pictures of a bubble, and I want to come back to the data evaluation. And I mentioned it on one of the first videos that we, for example, have reflections on a bubble surface, or maybe also some disturbance by shear. And in this project, we have the great benefits that we have the same data, and a lot of experienced groups came together to evaluate the data with existing codes. And then we asked ourselves the question, okay, do our codes give us the same results? And yes, successfully, for the bubble diameter, one of the major parameters, all the different evaluation codes we used in this project from the different groups give us quite similar results, which is quite fine. But looking to the contact angle here, also for a pool boiling case, we see that the evaluation code can have a quite significant effect on the data evaluation. So we have variations from 30 to 50 degrees, for example, between the different used codes. But also, out of time reasons, I want to talk too much about that and want to go too much into detail, because also Rania is preparing a publication on that topic, especially on the black and white data evaluation, together with all the other groups. And we hope to publish this paper maybe in March. So submit it maybe in February and publish it in March. But I want to also maybe get your attention on a plan we have with this data, because we thought maybe when we have this issue, maybe also other guys would have found it interesting. So we plan to publish not just the results of the evaluation, but also the raw data. So please feel invited, if the paper is published, to check the data and maybe to use your own codes you're using for bubble evaluation, and see what your evaluation code gives compared to the other ones. And a quite recent task we just started within this month, we thought about, okay, but especially in zero gravity, we have a superheated layer which will stay to the surface. But what will happen to this superheated layer, or what will it cause to our measurement? For 1G, as I mentioned in the first videos, you can see all this shear. But yes, for sure, in zero gravity, we don't have this because we don't have natural convection. So Alexei, one of our colleagues in the group, Alexei 𝗕𝗯𝗯𝗃, performed a first and simple calculation where he took the exemplary bubble in a 2D shape. And then let's say we just turn the bubble around, look at it from the side, and then we look at a ray starting at the bubble foot. And by the superheated layer, this ray will slightly bend by the different refraction index. But that would mean, on the other side, on the other hand, that the camera will think that the point seen will come from down here. So doing this not just for a point, but for a whole bubble, we just took a 6mm bubble, 18-degree contact angle as an example, a 1D temperature profile from the reference case, would mean that the bubble on our camera would look like that. So having a natural contact angle of 18 degrees, we would measure with a perfect working evaluation code of 30 degrees, which is also quite a difference. And yes, as this is not a conference talk, but a seminar, I just wanted to show what we're working on and maybe use it as a starter for discussion. So to summarize my talk, we performed the Multiscale Boiling Project over a period of 11 months within 2 measurement periods on board the International Space Station. With that, we measured over 3,000 measurement sets. And we could, I think, up to my knowledge, on the first time, implement pure fuel boiling and shear flow and electric fields in the same experiment to combine all the different acting forces. And what are our next steps? I also mentioned, yes, the reference papers has just published last week. We want to further publish, especially soon, the black and white evaluation paper, and also give you the opportunity to compare your data to our published data. Yes, and with this, I'm finished with my talk. Thanks a lot. Again, also not to all the audience, but also to the whole team who makes this project possible. Thanks a lot.
Thank you very much, Axel, for this very interesting, nice presentation. And I'm opening now the chat and, of course, the microphones to ask questions and discuss. So please go ahead.
Matthias, I will start with a question if anyone else want. So Axel, you, I don't believe whether you measure the fluid, but that's 𝗕𝗄𝗯𝗓𝗓72. Right?
Oh, it's 𝗕𝗄𝗓𝗓72, yes. Okay.
Anyway, and the question I have actually is in the comparison between the parabolic flight results and results on the International Space Station. If I understand, you tested a similar design concept on the 0G flight. And I was wondering whether you were able to make a comparison with the ISS results, and what did you learn from that comparison?
Let's say major outcome is that the small disturbances on board the parabolic flight are still too large to get the same results as on board on the International Space Station. So even the position on board a parabolic flight changes the gravity a bit because you will not have perfectly 0G in all 3 axes. So if you're sitting, don't have it completely in mind, but I think if you're sitting close to the cockpit, you still have a minor gravity towards the cockpit. Yes, because the airplane is not a point; it's a massive plane. So the bubble in the parabolic flight will move much earlier than on board the space station. But let's say the major tests which could be performed on parabolic flight were quite successful, because we also had to test if we can nucleate the bubble with the existing laser. Because yes, for sure, if you do it on ground, we have natural convection. We could also see that this has an effect, let's say on the minimum laser power we need to nucleate the bubble. Yes, maybe so to sum it up, it's really helpful to have this parabolic flights also to get the technique working, because when you're on board the International Space Station, you cannot change anything. So you have to test it before. But nevertheless, especially for pool boiling cases, the residual gravity on the parabolic flight is, let's say, too large to compare it over a long period of time. For a shorter period of time, let's say within the first second, it's still okay. I'm not quite sure about how this with shear flow and electric field. Maybe Polo and Katrine can comment on that. I've seen Polo. I don't know if one guy from Toulouse is here, but yes, at least for pool boiling, that's the way it is.
Okay, so we have a question from Han. So please.
Hi, this is Han Hu from University of Arkansas. Really appreciate it for this very nice presentation. Actually, I just read your paper on applied thermal engineering just last week. Google Scholar pushed it to me. It's such a masterpiece. I appreciate that. I have 2 questions regarding this microgravity boiling. One thing, my understanding of this is because you are using dielectric, I'm understanding this effect of the application of boiling is majorly for cooling of electronics. how about like in power systems? Do you also use boiling, for example, in the fusion surface reactors or any of these propulsion system?
Sorry, I think I don't got your question correctly.
So I'm trying to understand background question is where is boiling implemented and used in spacecraft or space applications?
Okay. Up to my knowledge, let's say pure boiling, like a pool boiling, is not used in space applications so far. What we have for sure is, I call it smaller brother evaporation, where we have a lot of the same effects. For example, an every heat pipe, which will be used on satellites or whatever. We once had a project together with a German company, 𝗕𝗃. They're also building satellite systems, and we did research for them for forced convection boiling loop for cooling. It was quite nice, but in the end they didn't use it because I think it was political reasons. But my personal feeling is that there's still a huge fear using these processes because they are not so well understood and proven as, for example, just a normal heat pipe or just heat conduction by whatever, copper or things like that. So let's say we do this research to change this.
Gotcha. Thank you. And I'm just trying to understand if that, like for example, heat pipes, heat rejection system is where we plan to use boiling, then our two-phase heat transfer. What is the most relevant working fluid? I'm thinking about in this way that in spacecraft, the out space is pretty like a cold, pretty low temperature, and then the reactors may have pretty high temperature, and that's what we want to take advantage of: high temperature difference, higher efficiency. And then I'm just thinking about the most relevant working fluid. For example, close to the reactor, maybe liquid metal would be more relevant. And then close to the rejector, what would that be, like pressurized water? Or
honestly, I don't know. This is still maybe 1 or even 2 steps in the future, thinking about especially these fluids for future applications. I would say the most advantage of these two-phase systems is the separation. So let's say the space separation. You can have your radiator, let's say, more or less far away from the heat generator, and you can just, let's say, pump the fluid even by itself. If you think about pulsative loop heat pipes or things like that, or by pump system with a shear flow, things like that. That's major importance, that you can completely decouple that and also cool several heat sources with the same loop, with the same fluid, and bring it to one separator. But yes, I guess we still have to do some of the research to give a really proven system for, let's say, really high-tech space application.
Got it. Thank you. May I have just one more question? So for this type of microgravity test, I actually contact a company called Zero-G earlier. They give us a quotation of around 10K just to run one parabolic flight test. But of course, that's pretty high budget. I'm just wondering whether there's any other approach, even just to testify the facility or device before performing a parabolic flight test.
I think this is what I tried to mention on my slide where manned lab parabolic flight ISS. So for sure, you have to do it on ground before, and then you have some possibilities for zero gravity, like for example parabolic flight, like drop tower, satellite systems, or sounding rockets, for example. But you have to choose, let's say, the system depending on your needs. So they have different gravity levels. So parabolic flight is, up to my knowledge, one of the lowest quality in gravity level, for example, compared to sounding rocket or drop tower. but it gives you the opportunity of a let's say longer term zero gravity or microgravity than the drop tower, and it gives you the opportunity to change something on the fly because you're in the plane. So, for example, if you tested the nucleation of the bubble with the laser setting, it's really helpful to do this in a parabolic flight because you can test it and then you see the result. And as a researcher, you can just say, okay, we go this way and we change this parameters, because if you have to program it everything in advance and you see you had a wrong assumption, maybe you will end up with whatever 15 experiments where nothing happened because you could not act on the experiment while you're doing it. So, but for sure, there are different opportunities for microgravity research. Yes, like drop tower, parabolic flight, sounding rockets, satellites. But you have to use the one which is most suitable for you or to answering your question.
Got it. Thank you so much. Really appreciate the comments.
Okay, thank you. In the meanwhile, a comment in the chat, a question from Edinburgh, from Professor 𝗕liche. In terms of energy balance, were you able to conclude where the energy required from bubble growth comes from, either superheated layer, micro layer, thermocapillary, etc.? Also, how succeeding bubbles on the same site influence each other growth in microgravity?
On the first question on the energy balance, we are still working on that. That was the reason on, maybe I can go back. Can I go back to the slide here? Just give me a second. I just have one screen, so I'm sorry for using the mouse to go through all the slides. Yep. What you can see here is, let's say, the huge difference in waiting time in the last column in here, with some quite strange numbers. For example, 6.66 was exactly chosen to answer this question. We're still waiting on the results, but we choose experiments in a way that we, for example, have the same heat input up to nucleation by different sources. So, for example, we have lower heat flux, but a longer preheating time. And so we, yes, let's say, set experiments to answer this question. But yes, I have to say that we, yes, still have to wait for that, for the answers, because we're still in the evaluation. And the second question, succeeding bubbles. If you're talking about pool boiling, they will mostly disturb the growth a bit, not the overall, let's say, diameter, because the small bubbles will more or less directly coalesce with a big bubble. But you have, let's say, some fluctuations on the surface of the interface. If you have shear flow and electric field, you like to have a next nucleation. So I would say the upcoming bubble is not influenced, the first bubble is not influenced by the second one. Maybe a bit in shear flow if you have not such a strong shear flow, because it's, let's say, first bubble is in the shadow of the second one. But this will especially be evaluated by our colleagues from France, the shear flow cases. So yes, we are still in the evaluation phase on that, if this hopefully answers your question.
Okay, perfect. So the next question from Mirko Manini: in microgravity, I assume that the thermal boundary layer at the heated wall keeps heating up and grows in thickness as time elapses. So subsequent bubbles may have different temperature fields around. Have you seen any impact on the growth rate of consecutive bubbles?
For sure, you see influence from the first to the second because of the laser. So the laser has quite, let's say, quite strong heating power, but it's just set on for 20 milliseconds for the, yes, initiation of the first bubble at the point, at the time where we want to have it. otherwise, I haven't seen a lot of that because comparing the thermal conductivity of the Fc72 and the 𝗲𝗃, you see that the 𝗲𝗃 is much more conductive. So the 𝗲𝗃 is more or less, let's say, at the same temperature quite fast as, let's say, the influence on the superheated layer of the fluid. So far, the evaluation had been performed. I couldn't see any influences, but I also invite all the other colleagues who maybe performed some evaluations I'm not aware of right now. But as far as I know, on the second, third, or whatever bubble, I haven't seen a huge influence of the temperature profile of the 𝗲𝗃. For sure of the fluid, but not of the 𝗲𝗃.
Okay, thank you for that. Any other question? Hello, Vladimir.
Yeah. Axel, thank you for a really nice talk. It's great joint work. I have a question about the operating parameters which you used. The maximum heat flux was only 1.5 watt per centimeter square. What about high heat fluxes? Since most of the devices used both on ground and in space deal with much higher heat power. And about the pressures range, it is not so wide. I mean, it will be very interesting to see what has happened during extra low pressures when the bubbles have extra large sizes even at normal gravity. Maybe you plan some further experiments on the boat.
So yeah, for the heat flux, we initially planned to go to 2 watts per square centimeter. But then we saw that we hadn't been able, even by a tremendous effort, to be sure that we not have parasitic nucleation on the surface. So maybe if you remember the shape of the coating, this was a bit tailored so that we have higher heating power in the center where we want to have it. So just keeping parasitic nucleation a bit away from that part. But in all the tests we performed, we saw that with 2 watts per square centimeter, we couldn't reach just a single nucleation by the laser shot where we want to have it. A second point was that we also destroyed some heaters in the lab because we put a lot of thermal stress. So building an experiment for ISS was also just building the heater for us at the institute quite challenging because we had to be sure that for the foreseen measurement period, which is several months from, let's say, bringing it to NASA to perform the last measurement, we wanted to be sure that we have, or let's say that we not overcome a maximum amount of non-condensable gas. So everything had to be quite tight and quite, let's say, yeah, fixed. So also the heater was implemented, let's say, in a press fitting, and sometimes we just get nucleate boiling, the onset of nucleate boiling at over 2.5, 3 watts per square centimeter, and by that we just broke the crystal by thermal stress. So we decided to reduce this requirement to 1.5 because this was secure operation, and it was more or less the same for the pressure because the Multiscale Boiling Project, I think it started 15 years ago about that, was putting a lot of requirements to the industry to put into this box, which was quite difficult. So in the end, we had to find a solution which was possible for, say, all the participants, also for either safety and the industry team. So bringing it to much higher or much lower pressures was just not really feasible for the given equipment. So if you remember the pressure bellow I mentioned on the schematic, the whole surrounding of the boiling cell, so the space between the boiling cell and let's say, yes, the housing was filled with SF6 gas, And this SF6 gas was used by a compressor or by a valve to set the pressure on the bellow. And yeah, you also have a limited amount of this gas, a limited power of the compressor. So just by technical reasons, it was not really possible to go to even higher pressures. Also by temperature, we could condense bubbles by 1.3 bars that we also used. And because we had to get rid of the vapor for the next experiment, so we performed an experiment, increased the pressure 1.3 bars, condensated all the vapor, and started the next experiments by lowering the pressure. Yeah, but to summarize, it was technical feasibility. For sure, it's interesting, and we tried to get more information with a parabolic flight. We performed parabolic flights with the same device, but a different fluid, for example, also different parameters. But yeah, for the ISS, this was all what we could get.
Okay, thank you. And what about the future experiments? Do you plan any experiments on heaters without artificial cavities, for example, to implement high heat fluxes and so on?
So far, we don't know if we might have the opportunity for a second flight because the fluid science laboratory will not work as it has worked in the past. So we discussed with ESA if there are some opportunities, but we don't know that. We have the experimental container in our lab right now, so it came back from the International Space Station, and we try to perform some experiments in the lab. But we have, yes, it must be a good cooperation with ESA and also with the industry team, because if we want to keep the opportunity for a reflight, we, let's say, cannot change everything because it has to fulfill flight safety and all these issues. So yes, we will see what we're allowed to do with the experiment and see what we can do in the future.
Okay. Okay, thank you and good luck.
Thanks.
Okay, thank you. Any more questions? Maybe a little short question from my side, Axel. You mentioned press fitting, but this particular sample in the Ruby was also press fitted, and the air gap was not prevented by any other glue or something between the section and the heater.
Correct. The crystal was fit quite tightly into a holder. It was a plastic holder. So this was especially not caused by the leakage requirement, but by the alignment. Because the requirement, I think, some years ago, but I think it was 300 micrometers from the center of the electrode to the cavity within the crystal. And yes, you have to go, let's say, the whole way around from the cavity to the holder of the heater, down the basement of the equipment to the electrode, then to the center of the electrode, and have a disalignment of 300 microns as a just the geometrical fittings had been quite tight.
Okay, perfect.
Mateusz, if there's time, I have another question for us.
Yeah, sure, Matteo, go ahead.
So, Axel, I actually wonder if you can tell us a little bit more about the project management aspects. Because this is a mega project in boiling. And I understand it started 15 years ago. Is that what you said?
Yes, I think this might be right. I think if you want to have a detailed date, you have to ask Lunis or Peter Stefan, because I haven't been at university at this time. Yes, but I think then the first ideas of this multiscale boiling had to come up in the scientific community in this group. Yeah. So maybe to the organization, maybe to summarize it, as far as I know, I just joined this project some time ago. More or less, you write application for ESA to do this research, either on parabolic flight or on International Space Station or whatever. If you're chosen that you can do that, you write a so-called ESR, Experimental Scientific Requirements. It's a basic document for all the partners. There's a scientific team that say writes down what they want to research, what the requirements are for this experiment, and ESA is searching for an industrial partner, building this experiment based on the requirements. For sure, you will have a lot of communication in between. Sometimes industry has some problems. Sometimes you also have some quite good ideas. Sometimes you have to change the ESR, as I mentioned. If industry come to you and say, you want to have so many data downloaded from the International Space Station live, and they tell you, but the International Space Station does not have this data bandwidth. So what to do? You cannot change that. So you have to change requirements or change the experiment. But let's say in some kind of this cooperation, in the end, you will hopefully come up to a working and successful experiment, which is sent to the space station.
Okay, Matteo, I think it's fine. Yeah. So next question from Paula, please.
It is not a question, it's rather a comment, since I'm involved quite deeply in this experiment, which actually started in 2005, you're right, Matteo. So many years ago. And also to answer to the questions of Vladimir, it's very difficult to make experimentation in space because everything gets very complicated. And think about that, just bringing down the module, the Ruby module from the space station to ground costed $2 million. Just to have an idea, just to have an experiment back in our lab. So it's extremely expensive. Everything is very hugely complicated. There were experiments in the past who failed just because the fuse blew and there was nobody able to replace the fuses, so the experiment was abandoned. So it's not so easy to plan a new experiment. The power budget and the cooling budget in the space station is limited. The space budget is limited as well. So it's not the same as being in lab. Parabolic flight offers more opportunities, of course. It is expensive, but you know that the European Space Agency offers possibility to make parabolic flight for European scientists and also scientists from Russia or other countries outside the European Union can join a team in Europe to perform parabolic flight. And in that case, you have just to spend to make the experiment, which is a little more than making an experiment for your lab. So it's not really so much expensive. Other possibilities are a sounding rocket, but very expensive as well. Opportunities are not so frequent. Or drop towers. Drop towers, the matter is time, because gravity, you know, is free fall. And free fall needs space to get time. And so you can make a drop tower for sure even in the staircase of your building, but you will have just 1 second of microgravity available, which is good maybe for studying a very short phenomena, but not for study long-term phenomena. So this is very difficult. I would like also to come back to the question of Mirko about the increase of boundary layer during the experiment. Actually, when we had pure boiling without any external stimulus like electric field or shear flow, we didn't get the detachment, or we got the detachment very seldom during the duration of experiments. Just a single bubble grew during the experiment. So the parameter which is affecting the thickness of a boundary layer is more the waiting time, which is still on the screen, which we tested, as you see, in several steps to the web. When we have electric field or shear flow, in that case, the bubble detachment causes the disruption of the boundary layer around the bubble. And as you know, the fluid is replaced by cooler fluid. So we attain a sort of regime, and the subsequent bubbles are more or less identical, as you saw also in the movies, compared to the first one. So the main parameter affecting the boundary layer thickness and also the energy balance is really the waiting time. not the fact that the bubble that detaches later is in a different condition than the former one. This is it. Thank you.
Yeah, thank you for these clarifications, Paula. Another question from Lund Tatrist. So please.
Matvek. Yes, just I don't want to ask a question to Axel because he knows and we know very well this topic and the results. I just want to say just few words about the management of the project, and just to say that the project was not very easy to handle because there were several teams, several steps, and so on. And for me, I am very happy that this project finally succeeded because we got results. And it is for me very important to say these results are unique. And I am happy that the team was very strong, and the efforts given by each member of the team leads to these results. Thank you very much for your presentation, Axel, for this, because you presented the project and with the results. But I can say that now we are really starting with all the group trying to analyze these results. And I think, I don't know this kind of results existing in the literature, and I hope that we will succeed to have a very original theoretical approach of this bubble growth. This is what I want just to say. Thank you very much for this.
Yes, thank you. Anyone else? I don't see any hands raised up. Questions? So anyway, it was very, very nice talk. Maybe we can start closing this session. It was 1 hour, 3 minutes now. Thank you, Axel, again for having this speech presentation. Thank you, Matteo, MD.
Thank you for being here.
And of course, also to 𝗕𝗓𝗯𝗃 to organize everything. Okay, everybody, see you next time. Keep in touch, check emails, and you will get an invitation for sure. Of course, don't forget to check the YouTube videos of current sessions on the TTC.